So next speaker is Pranshu. He will be talking about stochastic window.
So hi, I'll talk about stochastic window mean-payoff games. This is based on work I did with Laurent and Shivashish. So what are stochastic games? So we'll be looking at some games played by two players. We'll call the players player one and player two. In the literature, they are called the controller and the environment. So we'll look at zero-sum turn-based games that are played on graphs. So the graphs we'll call V, E, the vertices are V and edges are E. And we'll assume that the graph has no deadlocks, which means that every vertex has at least one outage. So here's an example of a graph, a game graph. So there are many shapes here. So any vertex that's denoted by a circle is controlled by player one. Vertices drawn in boxes are controlled by player two, and diamond vertices are called probabilistic vertices. So this is the setup. How is the game played? So the game is played by placing a token on some initial vertex, let's say V0, and then it's a turn-based game. So in each turn, if the token is on a player controlled by player one, like it's here, then that player chooses one of the successors. Let's say they chose this successor, and then the token moves to So now the token reaches V1, which is a probabilistic vertex. As part of the input, we are given a probability distribution over the out edges of probabilistic vertices. So over here, we have a distribution of 0.3 and 0.7 over these two edges. Now one of those two edges will be chosen according to those probabilities. Let's say the top edge was chosen. So the token moves to V2 and that turn ends. So in this way, we can record the path taken by the token. And this continues forever. Now, token is on V2, which is a player one vertex again. There's only one out edge, and the token moves along that edge. And now this is a player two vertex. Player two chooses one of them. Let's say they go down. Okay, let's say they went down. So this continues forever, and what we get is an infinite path in the game graph. This is what we call a play, an infinite path in the graph. Okay. So, but what is the objective of the players? So we'll look at a special kind of objective today, a quantitative objective called the window mean-payoff objective. So first we'll add some more structure to the graph. We'll add a rational quantity. We'll assign a rational quantity to every edge. We'll call it a payoff of that edge. So what happens is every time an edge E is traversed, player one receives that amount written on the edge from player two. It's a zero-sum game. Player one receives that amount, player two loses that much amount. And then corresponding to every play and every infinite sequence, every infinite path in the graph, you'll get an infinite sequence of payoffs. All right, so we would like to measure how good that is for player one. So obviously player one would like to receive higher payoffs, but we want to formalize that notion. One way to do that is to look at the mean payoff. So what we do is we want to see in the long run what's the average payoff player one gets in each turn, and we can take the limit. So what we can do is compute the total payoff you get in the first n steps, and you divide by n. That's the total payoff in the first n steps, and you take the limit as n goes to infinity. Do this, and this is what we have. So the limit as n going to infinity, the total payoff in the first n steps divided by n. This is
so it's the payoff of the first player.
This is the payoff that player one receives from player two.
So the second player chooses the numbers. I mean, this utility of the edges.
No, the edges is given. The weights are given as input.
So what's the role of the player two?
So whenever there's a whenever the token reaches a player 2 vertex, a box vertex,
Ah,
they select where to move the token to, whether they move to V2 or to V5.
okay. And this probability
It's also given.
but that is also giving some payoff. What is the role of that?
This is to introduce like randomness in the game.
So it's like kind of expected payoffs.
Right? So let us say a play is good for player 1 if the mean payoff of that play is non-negative. So on average, player 1 is receiving more than they are paying. So however, there are some downsides for this objective. A play might miss.
Sorry,
Yes.
here is in the formula there is no probability or expectation.
So this is for a given. So yeah, so this is for one given play. Once you fix a path,
Pi is a path.
Pi is a path.
It's not okay.
Once you fix a path, you see how well it does, and then we'll see what's the probability of getting that path. Yeah, one downside of this objective is that even though you're in the long run, you may have non-negative payoff, you can construct plays where you have arbitrarily long stretches where player 1 only sees negative payoffs. So consider this play, this 1 minus 1 and this 1 plus 1, then 2 minus 1 and 2 plus 1, 3 minus 1 and 3 plus 1, and so on. So eventually you'll find like 100 minus 1, some 100 plus 1. So we would like to strengthen this objective. So we want to say that we'll assign some window length, say L. Player 1 would not like to remain in the negative for more than say L steps. So that's where we get a window mean payoff. So I'll define what are windows formally. So for every vertex in the play, you find out the number of steps it takes for the total payoff from V to become non-negative. So suppose you start at V0, we want to see how long the payoff remains negative for. So we'll start computing the total payoff from V0 and see when it first becomes non-negative. So it is you saw -2, -3, -1, +1. The total is still negative. So we keep going, and the total becomes +2 here. So this is where the total became non-negative for the first time. So we say that the window starting at V0 closed at V6. So player 1 was in the negative for 6 steps. And then we do this for every vertex in the play. So we see how long windows remain open. So this window remained open for 6 steps, and then this remained open for 4 steps, so on. Now we come to our objective. So the objective we are interested in is this. So player 1, a play satisfies the direct window mean payoff objective if every window in the play closes in at most L steps. So you're given a play, it's good for player 1 if like from any point in the play, your no window remains open for more than L steps. So like this is the objective of player 2 then. So a play does not satisfy this objective if the play contains even one open window of negative. So here's like an example. So suppose L is equal to 3.
Until this point, the probabilities for the randomization
No, not yet. That will come after this. So once we understand the objective, we'll see what is the probability of getting an objective.
So just for open window means you have negative payoff or
The number of steps it takes for your payoff to become non-negative. So if your window is open for L steps, then it hasn't become non-negative in L steps. So for example, here's one play. You start in V0, you go to V1, V2, and then you loop in V2, V3 forever. And suppose our window length is 3. So does this satisfy our objective? So no, it does not. So if you consider the window starting at V0 itself, and you look at the next 3 payoffs, -2, -2, -1, it does not, it's negative. So the window does not close in 3 steps. In fact, that window never closes. and it does not satisfy this objective.
So what you want to find
So given an infinite path, I want to know if it is satisfying the objective or not. So from
So
I'll come to that. Eventually, we want to find an optimal strategy for both those.
Okay.
so
I'm defining the objective now.
so the path is infinite, so you are given as an oracle kind of. So like oracle access to that. I mean, so infinite thing. So
No, so we are given this graph that,
no, but
and we are given this window length L.
yeah, I got it.
Okay. Yeah, this is an example of a play that satisfies the objective. I think you can see that. This has, I mean, all payoffs on this path are non-negative except this. So the path is like this: V0, V4, V5. You take the self loop once, and then you come to V6 and then V4 and V5. You take a self loop. So the windows starting at V5, it remains negative for one step. When you take this loop, the payoff is -1, but when you reach V6, it becomes, the total payoff becomes non-negative. Yeah. One final example, consider this cycle: V0, V4, V5, V6, V0. Does this satisfy this objective? No? Why? Right, starting from V6, you see -2, 0, +1. Here, in 3 steps, it does not become non-negative. So this does not satisfy the objective. So even if you see one open window of length L in the play, player 2 immediately wins. This may be a too strong condition for player 1. So we weaken this objective now for player 1. We come to a final objective, the window mean payoff objective. So we say that a play satisfies this window mean payoff objective if eventually all windows are closed in L steps. So you are allowed to see open windows of length L for some finite amount of time, but after that, every window should close in at most L steps. So what would be the negation of this? So when would player 2 win? So player 2 would win if the play contains infinitely many open windows of length L. So this way you will have no finite prefix that you can delete and just see all windows of length L. Okay, so you can see the same examples again. So this did not satisfy the direct objective. It still doesn't satisfy the weakened version either.
So, but once you remove the initial.
Oh yeah, yes. Oh yeah. Once you remove the initial one,
Then you are just moving on to V3.
yeah, then it's satisfied. Yes. And this satisfied the direct case, so it also satisfies the indirect case. And this didn't satisfy the direct case, but it also does not satisfy the indirect case because you keep visiting these 6 infinitely. Okay, so we'll come to a decision problem finally. So you're given a vertex G that the game begins from. You're given a window length L. And if the game begins from V, then the question is, can player 1 satisfy this objective with positive probability? So does player 1 have a strategy such that no matter what player 2 does, for all strategies of player 2, in the resultant outcome satisfies this objective with positive probability. Okay.
So eventually, when you're saying eventually all windows close, that means earlier I thought you were taking the cumulative amount and then checking if it is becoming negative. So when you're starting windows, are you starting the amount cumulated from that point?
So I mean, eventually after some point you check.
Like the first window never closes, so that will not.
The first window never closes. Yes.
So
eventually means if there exists some suffix of your infinite path which satisfies the direct.
Okay, so you're taking the cumulative amount starting from V2 itself. Okay.
And then other problems that we can look at are Thus, can player 1 satisfy the objective with probability 1? We'll call this the almost sure decision problem. And the general problem is, can player 1 satisfy this objective with probability at least 3? So one useful theorem is determinacy, which says this. So for any vertex V, you either have one of these. So either player 1 wins from that vertex or player 2 almost surely wins. To see this, so either player 1 wins with probability, some positive probability, or player 1 wins with probability 0. So what this theorem is saying is, when player 1 wins with probability 0, it means that player 2 is winning with probability 1. So that needs to be proven. It requires some knowledge of oral algebras. We'll just
Okay. I want to make a comment here. This one, I mean, so if you look at this problem, so let's say you will present this problem in a very particular fashion. So let's say, okay, I want to ask you this question. Can you associate a single scalar variable that will tell you whether the window closes or not? So I give you a path, and at every point I am just accumulating some scalar variable. And just looking at the scalar value, I'm going to decide, right? So I'll give you a sequence of these numbers, right? And I want to decide whether this condition is satisfied or not.
okay.
Right? So what do you think? So the answer is yes. So there does exist one, right? And it is related to linear regression. And most likely, so whatever you can see that this positive probability 1 or probability at least 3, whether this is satisfied or not, this is nothing but related to the stabilization problem, that is whether the Markov chain, so there is a corresponding Markov chain.
Once you fix the strategy of both players, you'll get a Markov chain.
Yes, you have a Markov chain. No, I'm talking about that specific scalar values only. I mean, this will satisfy a Markov chain. I can tell you what is this random thing is. And the question is whether this Markov chain is recurrent or not. It is, and what kind of recurrence it is, right? So if you can find a policy that stabilizes this thing, so in general this is called Q's, right? It satisfies the linear regression, then it will satisfy solve this problem.
Right. How do you get the scalar values?
This is linear regression. So you just do okay. So this evolves like qt plus 1 equal to max of 0 qt plus the value. So it will give you the so if you just under this regression, it's the sum over all cumulative sum starting from time t. Right? So if you can, so this is like so you're looking at this, I'm scanning at time t. And I'm starting from time t, I'm just adding xt plus xt minus 1, xt plus xt minus 1 plus xt minus 2, and I'm taking super of all of this. So this is exactly what this QT is. So now if this quantity QT is, let's say, larger than equal to 3, that means that there are concentrations going outside length equal to 3. And I think it's 5 seconds.
Okay. And yeah, think about that. But
yeah, okay. We can definitely discuss this.
We can discuss this later. So given a vertex, we want to find out if player 1 can satisfy their objective with some positive probability. So what we'll do is we'll find the positive and almost sure winning region. So there are some set of vertices from which player 1 wins with positive probability. We'll find that region. So I'll briefly describe the algorithms for how to do that. We used ideas from some older papers for that. So we used these ideas from this 2009 paper to show how to reduce stochastic games to non-stochastic games. So a non-stochastic game is a stochastic game where you don't have any probabilistic vertices. So those are a special case, and we know how to solve those. And so in this 2015 paper, we saw how to solve this objective for non-stochastic games. So we'll combine these two ideas to solve stochastic games with window mean-payoff objectives. And here's the I'll come to that, but first we'll require this to know what's a positive attractor.
What is stochastic game for the non-stochastic game?
So what I described was stochastic games.
Uh-huh.
So a non-stochastic game is a special case of stochastic games where you don't have those diamond vertices.
Okay.
No probabilities. Deterministic. So this is one thing that I need to define. So what's a positive attractor of a set? So a player one positive attractor of a set is the set of all vertices from which player one can ensure that the target set T can be reached eventually with positive probability. And this can be computed by a fixed point computation. So suppose we want to compute the player one positive attractor of this set V2. So we can compute this iteratively. In each step, what you do is you check what are the vertices from which you can reach your target set in one step with positive probability. So and you start with V2 already in your target set, and then you can reach V2 in one step from V1 and V3. However, like from V1 with positive probability, with probability 0.3, you can reach V2. However, from V3, it's a player 2 vertex. Player 2 can decide not go to V2, go to V5 instead. So that won't be included in our like running set. We have updated our set to V1 and V2, and we can repeat that again. So from V0, you can reach V1 with positive probability. However, from V3, you may not reach this green set. So we don't include that. And we continue this until we reach a fixed point. From here, we won't include any of these again. We have reached a fixed point. So from these three vertices, you can reach V2 with positive probability. So this is the player one positive attractor of V2. So I would like to note that the complement of a player one positive attractor, like the vertices that are shown in red, is a trap for player one. So if the token is in one of these red vertices, then player two can ensure that it never reaches the green vertex, never leaves the red area. And finally, suppose you are given a stochastic game G, okay? I would like to define an adversarial non-stochastic game corresponding to G. Let's say GNS. All I've done is you look at all the probabilistic vertices in G and you change them to adversarial, player two vertices. So this is much better for player two. So where there was a probabilistic vertex, if there's a player two vertex now. So if player two can win. So if player one can win in this non-stochastic game, they can also win in the stochastic game. Okay. I'll give an outline of the algorithm to compute the winning region for player one. So what you do is, this is a recursive algorithm. So we would like to output the positive winning region for player one. I'm denoting our objective, the WMP objective with 5 for short. So this is an algorithm to compute the winning region for the same objective in a non-stochastic game. This we have from the 2015 paper, and we'll use it as a black box in this paper. So let W1 be the winning region for player one in the adversarial non-stochastic game corresponding to G. Okay, and so there could be two cases. So either W1 is empty or it's not empty. Suppose it's empty, in which case we return empty. That is, player one does not positively win from any vertex. That is, player two wins almost surely from every vertex. So the other case could be if W1 is non-empty. So what we do is we compute the player one positive attractor of W1 and call it A1. And we return A1 with the union of the same algorithm called on the remaining graph. So what's happening here? So W1 was the winning region for player 1 in the adversarial game. So if player 1 is winning in the adversarial game, they're also winning in the stochastic game. So everything in W1 belongs to the positive winning region. And everything in the positive attractor of W1 also belongs to the positive winning region, because once the token reaches A1, what player 1 can do is they can ensure that the token reaches W1 with positive probability, and then they start playing with the winning strategy in W1. And as I described before, the complement of a player 1 positive attractor is a trap for player 1. So this game that you see, V minus A1, is a trap for player 1. And this is also a valid subgame, and we recurse on this subgame. We repeat, like we repeat this until we this like algorithm finally terminates when W1 is eventually empty in some subgame, and that we denote as the almost sure winning region of player 2. This is all the positive winning region of player 1. Yeah. So this algorithm eventually terminates because in each step of the recursion, we are calling the algorithm on a smaller subgame. In the worst case, it runs for at most V many times. Yeah. It is also possible that player 2 does not win almost surely from every region. This is another possible ending. All right. So this one thing that to prove the correctness of this algorithm, we need to show that if W1 is empty, then indeed player 1 does not win positively from any vertex, which is what we showed in our paper. So you recall that GNS is the adversarial game. So just because player 1, it's not immediately clear why if player 1 does not win in GNS, it implies that player 1 does not win in G. So this requires a proof. So I think it might be easier to see this statement written, the contrapositive of the statement. So what we'll show is this. So if player 2 wins from all vertices in GNS, then player 2 almost surely wins from all vertices in G. And the overview is this. So we'll start with a winning strategy of player 2, that's winning in all vertices in GNS. And we'll use that to construct a strategy that is almost sure winning for player 2 in all vertices in the stochastic game. So what are the issues in this proof that we had to overcome? Yeah, so note that player 2 can control fewer vertices in G compared to GNS. And with positive probability, deviations may occur in the probabilistic vertices. So consider this game. In the non-stochastic version of this game, suppose whenever the token reaches V1, player 2 would like to move the token to V2 in the adversarial game. However, when we look at the same game in the stochastic sense, the token may move from V1 to V3 with some positive probability. And this may cause player 1 to lose. So what we do is we construct a new strategy of player 2. So whenever an incorrect transition takes place in the stochastic game, we reset. That is, we forget the history that happened before the deviation. So player 2 starts playing as if the game started from V3 itself. So I only have 5 minutes. So this slide describes how you can construct a reset strategy. I'll just gloss over this. So what basically happens is this is a Mealy machine. This is how we usually encode strategies of players. So each transition is labeled by an input-output pair. The input denotes the vertex that the token is currently on, and the output denotes the successor that the player should move the token to. And what we do is we identify some transitions in this milling machine that are never taken in the adversarial game. We delete them and we add reset transitions in their place. So what we are trying to do is that whenever a deviation occurs, we reset, and the probability that no deviations occur for L steps is at least some positive quantity p raised to L. So this shows that an open window of length L will eventually occur with probability 1, and player 2 will in fact win with probability 1, which is what we wanted to show. Yeah, then that algorithm was to compute the positive winning region of player 1. We have a similar algorithm to compute the positive winning region of player 1. Sorry, the almost sure winning region of player 1. And you'll see that the algorithm looks pretty similar to what we had for positive winning. So almost sure winning for player 1 means positive winning for player 2. So that's why there are some similarities. I'll gloss over this. And then we'll have a similar lemma for this as well, but however, we don't need to prove that lemma because it turns out to be a special case of a theorem from an older paper.
Can you swap the role where player 1 and 2 and solve it for
Yeah, so that does not work because the nature of the objective is not symmetric. So what player 1 needs is to keep closing windows, always close windows in L steps, and player 2 needs to eventually close window again in L steps. Okay. All right. Yeah, so the final result is, so this is the result we had for non-stochastic games. So if you want to compute the winning regions for players in non-stochastic games, it can be done in poly time in the size of the input, as long as you're given window length in unary. And if this is let this be denoted by C, then to compute the positive winning region of player 1, this can be done in V times C, because a call to the non-stochastic version is made at most V times, because our algorithm runs at most V times. And the almost sure winning region can be computed in at most V square C times, because this in fact calls the positive winning region algorithm once. And this is our final result, that the positive and almost sure decision problems for window mean-payoff are in V time, and memory required for both places no greater than non-stochastic games. Yeah. And the value problem, this is a 2009 result, that if you have a prefix-independent objective, then, and if the positive decision problem has an oracle A, then your value problem is in NP to the A. And we have shown that our positive and almost sure problems are in P time. So our value problem is in NP to the P intersection co NP to the P, which is just NP intersection co NP. Yeah. Skip this. So conclusion is this. So I'll just say this. So what we did was we also managed to extract a property for which given an algorithm for a non-stochastic game, you can then make this similar reduction to stochastic games. And you only incur a blow up of V and V square. And we call this the sure almost sure property. And we follow the same algorithm. So in the algorithm, we made no use of the window mean payoff property. We just used phi. And yeah, you can then compute the positive and almost winning regions. Okay. Yeah, so we have this SAS property in which you can reduce stochastic to non-stochastic games with the V square blow up. And we have shown that these are in P and NP intersection co-NP. Yeah. We also looked at another objective and showed that they are in NP intersection. I have skipped that, but yeah. And we only looked at like probability satisfaction. So if player 1 can satisfy this with positive probability or not. what we could also look at is what's the expected payoff that player one can aim to achieve. Yeah. Okay. Thank you.